Okay, hi grade 12s. We're moving into the next little review video, and this one has to do with intramolecular bonding. So we're going to look at what happens with these bonds that are inside of a molecule. What are the names of them? And then I'm going to do a little review on how to draw these molecules and then think about polarity a little bit as well. So we're leading into a few other concepts that are going to take us into the rest of the unit. We'll come back to some of these as well. Okay, so this little segment is on intramolecular bonding, pages 9 and 10. Okay, so these are the inside bonds, remember? They are different than intermolecular bonds, and we often refer to them just as IaM bonds. So these are the inside bonds that form. They're either covalent or they're ionic, and if they're covalent, if they're a shared pair of electrons, they can be polar covalent or just non-polar covalent. It depends on the type of atoms that share those electrons, okay? Remember that these are the bonds that break when you have a chemical change, because during a chemical change or a chemical reaction, the inside bonds break, the atoms rearrange, and new inside bonds form. That's the definition of a chemical change. You can only have inside bonds breaking in order to rearrange those atoms so that you can make new compounds. So I want you to think about that at the molecular level, okay? And understand that a chemical change occurs. You have to make something new. So in order to make something new, you got to break those bonds. And we're going to look at the names of those bonds specifically from things you did in grade 11. Okay. So inside bonds, if there is an equal sharing of those bonds, that means that it's a covalent bond. And if it's between two non-metals that are identical, so between a carbon-carbon or between a hydrogen-hydrogen or an oxygen-oxygen, so you can think of those diatomic molecules, the name of that kind of bond is a nonpolar covalent bond. So we always describe bonds as best as we can with the most amount of detail, so that then you you show your understanding of the type of bond. And again, give some examples of that. So please go ahead and fill in. Do at least 6 different ones. Of course, you could do all the diatomics, but think of some of the other molecules that also have nonpolar covalent bond. It means that each atom shares the electrons the same amount because they are the same atom, so it has the same pull for the electron that it's sharing. So that pair of electrons, if you will, is right in the middle, and there's no polarity to that bond. Okay, compare that to the other kind of covalent bond where you have what we call a polar covalent bond. Okay, you have polarity to that shared pair of electrons. It's an unequal sharing, and you get that when the two non-metals that make up that bond are different. Okay, so CLF is a great example, and I'm going to get you to fill in a few more, right? There's a whole bunch of them you can use. Any example will work. The third kind of bonding that we have is our ionic bond. And this is the one, of course, we have between our metals and our non-metals. It's so extreme of the sharing that they don't even share. They actually transfer their electrons, remember? And then between the metal and the non-metal, you have ions because of that extreme sharing that one actually takes it from the other one. Then you have an electrostatic attraction between them. So go ahead and write down 6 examples of some ionic bonds, and that should be fairly easy as well. Okay, so we're remembering what those specific types are called. Now, we're going to look at, in general, covalent bonding, and in more detail what's actually happening between these, and we're going to look at that polarity. So go ahead and read through this little fill in the blank, fill your answers in, and then we're going to move on to showing what this looks like using an electron dot diagram and what are some of the general rules for this. Okay, so the rules are on the bottom of page number 9, and then we're going to actually do the work on the top of page number 10. So let's draw an electron dot diagram and then a line diagram for ethylamine. We have a compound, a molecular compound. It's made up of all nonmetals, 2 carbons, 7 hydrogens, and 1 nitrogen. Let's show how these atoms will combine together using our rules for how to draw this compound. All right, so here we go. We remember the carbon has 4 bonding potential electrons. They are a 4. Unpaired electrons, they have 4 valence electrons. Same, right? We take our information in the periodic table, and now we're going to apply it. Nitrogen's in group number 5. It has 5 valence electrons. That means that it has 3 potential unpaired electrons that could potentially be bonded. And hydrogen, of course, has 1. When you are combining electron dot diagrams, it's often best to show them using different symbols. You can use circles, you can use X's. It really doesn't matter as long as you can show your work for how you do this. So step number 1, what you're going to do is you're going to combine the 2 carbon atoms first. Why? Because based on the rules that you've read above, they have the most number of electrons to complete their octet. So I know that carbon and carbon are most likely going to be bonded together. So I'm going to draw my 2 carbons side by side, and I'm going to show there a shared pair of electrons right here. The way we show that using our Lewis dot structure for a molecular compound where this is a covalent bond is to put a little sharing circle around them. Okay? Shared electrons. That's what that means. Remember, if we were doing ionic, and I have an example down at the bottom, how do you show your work? This is what you did back in grade 10. How is ionic different? You show your Lewis dot structure. You show the transfer of electrons, because that's what happens when you have a metal and a non-metal come together. Then you show your ionic charges. And then you show the compound in the ratio that fits the zero-sum rule. Okay, that's your review of ionic. We're not doing ionic for this example. We're looking at a molecular compound, and we need to review how to share, or how we show those shared pairs of electrons. So remember, always remember, what is it, the topic that we're dealing with right now? And then how do I put that into some of my previous understandings when it comes to the different kinds of particles that we have. Okay, so I'll leave this on the bottom of my diagram so you can refer to what the difference is, how we show that for ionic versus how we show it for the molecular compounds. All right, so back up to the top. We've shown our 2 carbon atoms side by side. That's how you know carbon is going to be bonded to another carbon. Then, according to the rules, I'm going to combine nitrogen with one of the carbon-carbon partial molecules, again, because nitrogen has 3 unpaired electrons, okay? There are 3 potential spots for a bond, so I know that one of those is going to have a shared pair with that other one for carbon. Okay, there we go. There's another covalent bond we can form. And then there are 7 single unpaired electrons on the molecule. Can you see those there? Right? 1, 2, 3, 4, 5, 6, 7. This nitrogen already has its double pair there, so it's not gonna bond with anything else. It's quite stable as it is. And so now I'm going to add in my hydrogens to show that. I then take the next step, which is to convert my electron dot diagram to a line diagram where each line shows a covalent bond. Again, this is very different from how we do it in ionic compounds. We don't build molecules with our ionic particles because that's not how it works. We build crystal structures with those. It's the molecule kits that we use to build molecules, and so you do that by doing your electron dot diagram, show that single bonds that we've got as line diagrams, a line, okay? And then you could build the molecule based on that. So the line diagram is for covalent only. Covalent meaning non-metal, 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 right? That's all we're dealing with for these examples. So let's give it a try. Can you make a bond for the CH3Cl using those naming or the rules before? Go ahead, draw your electron structure, understand that you're going to have a bond between carbon and chlorine. Why? Because you start with carbon, then you do chlorine, and then you fill up the rest with your hydrogen. What does that line diagram look like? Okay, so you're going to take your Lewis dot structure. Okay, again, this is called your electron dot diagram. And now you're going to do a line diagram. Sometimes chemists will call it a Lewis diagram. The other name for it is a structural diagram. We're going to draw what that looks like. We're going to add in the names of the bonds, and we're going to look at the overall polarity of the molecules. So we can take our basic understanding add on all the things we had learned about in grade 11, and now we have a molecule that we can then talk about its physical chemical properties moving forward. Okay? And in fact, in this unit, we're going to now look at the names of what these structures look like, the shapes of the molecules. Okay, so here we go. I have my carbon, I have my chlorine bonded to hydrogen, hydrogen, and hydrogen. I'm going to put my valence shell electrons around the carbon, or the chlorine. Okay, and now I'm going to describe these bonds. What would you call the name of that intramolecular bond? It's between two non-metals that are different, so you have you have a difference of sharing between them, and so you have a polarity of that bond that is a polar covalent intramolecular bond. Okay, this is also the same. It is also called a polar covalent intramolecular bond. Okay, let's draw that molecule with the polarities. Okay, I'm going to show you how to draw a three-dimensional structure, but this is obviously another lesson too. Okay, so it doesn't matter which way you start your molecule, but you're going to have two atoms on the same plane. So if this is a 3D drawing, I'm going to have two on the same plane. I'm going to have this hydrogen coming towards me and this chlorine going away from me. All right, that shows that this is a tetrahedral structure. Again, we're going to get into that a little bit later, but I can show the bond polarities and I can show the molecule polarity as well. Okay, so I'm just going to get rid of this diagram, or the arrows here, for a second. I'm just going to put those back onto this diagram because I want to go back and use this diagram here to show the polarity of the bonds. Which one will the electrons be held closer to? Okay, do you remember this? We would have reviewed this on your periodic table, so go back to your periodic table and find which ones are the greatest polars of electrons, the electron affinity, if you will. Okay, we know that the shared pair of electrons between hydrogen and carbon are closer to the carbon. Carbon is more electronegative. This way. But what's the difference between the carbon and the chlorine? Can you tell which one? Chlorine. Okay, so you can see there that those are showing our bond polarity. Okay, that just shows our bond polarity. And that's how we knew that they're polar covalent, because they're covalent, shared between two nonmetals. Which one holds the electrons closer to it? The one that's most electronegative. Show the arrow that shows the direction of which one has the most electrons closer to it. And then overall, what would be the polarity of this molecule? Does it have a slightly polar side or not? It does. You can see that most of the electrons are towards the chlorine. So if you drew your chlorine to the right like I did, you're going to draw a big fat arrow, slightly negative this way, slightly positive this way. Our molecule has an overall polarity to it as well. Okay, let's do the next one. Okay, I've done my Lewis dot structure, so you catch up with me. Pause the video, draw your Lewis dot structure, and then catch up and check the answer with me. Okay, and what do you see? We have a single bond, two single bonds, we have a double bond here. So let me add a little bit of context to our diagram. How would you describe the bond between the two nitrogens? We have two shared pairs of electrons. That creates a double bond. Is it polar covalent or just covalent? It is a non-polar covalent intramolecular bond. The bond between the nitrogen and the fluorine holds the electrons closer to it compared to the nitrogen because fluorine is more electronegative. Here you have a polar covalent intramolecular bond. And then because you have a polar covalent intramolecular bond going this way and a polar covalent intramolecular bond going this way, where they have equal magnitude, same strength because it's between the same two atoms, nitrogen and fluorine on this side, nitrogen and fluorine on this side. What do you say about the overall polarity of the molecule? The overall polarity of the molecule is non-polar because they have equal magnitude, opposite directions. They cancel each other out like you would cancel out vectors in physics, and you have yourself a non-polar molecule. Okay, let's just jot that down. There is no overall molecule polarity because they are equal magnitude and opposite direction, and they cancel each other out. We will go over this in detail in a little bit later on too, okay? In 2 more lessons for now, we will come back to this idea. But right now, I want you to get a sense of basic terms for that, okay? All right, that is inside bonds, those intramolecular bonds. Let's move on to the next bit, which is the quantum mechanics model, and I'm going to do a little review with you now.